Hello, I am Thavamani Govindaraj from Tampere University. The title of my today's talk is A Finite Dimensional Controller for Robust Output Tracking of an Euler-Bernoulli Beam. This is a joint work with Pekka Humaloja and Paunonen. This is the outline of my talk. I will start with some introduction, then problem formulation, then I will discuss the solution methods used to solve the problem, and then we will see some simulation results. Let us start with the introduction. We consider output tracking problem of an Euler-Bernoulli beam, in particular a cantilever beam. There are results in the literature dealing with output tracking of an Euler-Bernoulli beam. Those results use infinite dimensional controllers, in particular observer-based controllers. In this work, our goal is to construct a finite dimensional dynamic error feedback controller such that the output of the beam system tracks the given reference signal asymptotically. We consider two cases. As the main problem, we consider the beam with boundary control and boundary observation. We also consider the case where the beam has distributed control and observation. In this talk, we will focus on the case where the beam has boundary control and boundary observation. Due to time limit, we will not focus on the case where the beam has distributed control and observation. So let us go to problem formulation. The beam system that we study is given by these partial differential equations. Here, the second line corresponds to the clamped end boundary conditions, and third and fourth lines corresponds to the free end boundary conditions. As we mentioned, we consider the boundary control and boundary observation. Here, we consider shear force control input, and as the output, we have the velocity at the free end. Here, the physical parameters rho and EI depend on the spatial variable psi, and they satisfy these conditions. Our goal is to construct a controller such that the output y of t tracks the given reference signal asymptotically. The reference signal to be tracked is of the form given by this equation. Here, omega k's are known frequencies, and ak and bk are possibly unknown constant coefficients. The dynamic error feedback controller to be constructed is of the form given by these equations. Here, Q represents the number of frequencies in the reference signal. Then the robust output regulation problem is given as follows. Choose the controller parameters G1, G2, K and K1 in such a way that the closed loop system is exponentially stable. There exists alpha greater than 0 such that for all reference signals and for all initial conditions, we have this term containing the difference between the output and the reference signal belongs to the L2 space. And if the closed loop system is exponentially stable, despite uncertainties, perturbations, and disturbances in the system, then the tracking is still achieved for all initial conditions and some alpha tilde greater than 0. Next, let us discuss how we solve the problem. Our aim is to use an internal model-based controller based on Reberber and Weiss, where the controller is constructed for exponentially stable, well-posed linear systems with positive transfer function. So in order to use the controller in Reberber and Weiss, we have to show that the considered cantilever beam is exponentially stabilizable and well-posed, and it has positive transfer function. We use abstract boundary control systems as a tool to verify these properties. The beam system can be written as a boundary control and observation system in the form given by these equations on a Hilbert space X, input space U, and output space Y. Here, calligraphic A, calligraphic B, and calligraphic C are linear operators. To show the exponential stabilizability of the beam system, we use directly a result from Guo. So in Guo's result, it is shown that the considered cantilever beam with negative output feedback is exponentially stable. So we can use directly those results to verify the considered cantilever beam is exponentially stabilizable by negative output feedback. Next, we show that the beam system is impedance passive. We can verify the input and output spaces are equal and the triple ABC satisfy this inequality. So therefore, the beam system is impedance passive. Next, we have a theorem showing that the boundary control system defines a well-posed system node. Here we give an outline of the proof. The idea is the boundary control system defines a system node and the transfer function of the system node is bounded on the complex right half plane. First, we argue that the boundary control system defines a system node given by this operator with domain given by this set, where the operator B is uniquely determined by the relation given by this relation on the domain of A. Next, using the results from Guo and Guo and Luo, we verify that the operator B is admissible and the eigenvalues of this restricted operator satisfy the spectral condition given by this inequality. This implies that the transfer function of the system node is bounded and hence the system node is well posed using the results from Stefan's. So we have shown that the beam system is exponentially stabilizable and it is a well-posed linear system. In addition, the impedance passivity of the beam system implies that its transfer function is positive. So we can use the controller in Reberber and Weiss for the robust output tracking of the beam system. Here we consider a particular reference signal sin 2t plus cos t for robust output tracking of the beam system. So the frequencies are 2 and 1. And based on Reberber and Weiss, the controller parameters are chosen by these matrices. Here G1 contains internal model. That is, it contains the frequencies from the reference signal. And the other parameters are chosen such that the closed loop system is exponentially stable. Choosing some initial conditions for the beam system and the controller with constant physical parameters, we have run some simulations. We can see that the tracking is achieved asymptotically. We have also plotted the velocity profile of the controlled beam system. So it is time to conclude. We considered robust output regulation problem of a cantilever beam. The problem is solved using a finite dimensional internal model based controller. We discussed the case where the beam has boundary control and boundary observation. The same controller can also achieve robust output tracking of the beam with distributed control and observation. In this case, the beam system is strongly stabilizable. The closed loop system is strongly stable and the rate of error convergence is not exponential. The advantage of using this controller is that the controller is simple and able to handle spatially varying parameters. Here we have added the main references that we use to solve our results. Thank you.